we will change to a new topic that is replacing environmental harmful processes by laser surface texturing, sorry, Syntecs project and applications. The presentation, as you are already seeing in the screen, will be made by Avish Gadam from University of Birmingham, also a partner in Syntecs project. And Avish is a project manager at this university, and his expertise is on laser surface functionalization, and currently is contributed to contributing to three European Union Horizon projects and one ERDF funded projects that University of Birmingham is participating in their activities. So welcome, Anvesh. Thank you to be here for the presentation. If you want, you can start your presentation, say something additional for yourself, and let's see the presentation.
Yep. Thank you, Pedro, for the kind introduction. So, as Pedro mentioned, my name is Anvesh Gadam. I'm a project manager at the University of Birmingham, and title of my presentation today is replacing environmental harmful processes by laser surface texturing. So these are the contents of my presentation today. First, I'll introduce a bit about what is called laser surface functionalization, then how we can achieve different micro and nano topographies at different scales with technologies such as direct laser writing, laser-induced periodic surface structures, and direct laser interference patterning. Then I'll talk a bit about what are the competing technologies with respect to the laser surface texturing. And then I'll introduce what we are doing in the Syntecs project with respect to the title, which is replacing harmful environmental processes with laser surface texturing. And I'll take one of the case studies from the Syntecs projects, which is a complex vapor chamber, and I'll talk about what we are doing in this particular use case, and then I'll conclude my presentation. So, so what is laser surface functionalization? As we've seen in the previous presentation, there is a difference between how the material removal with continuous lasers and pulse lasers. But in this presentation, I am focusing only on the pulse lasers, which are especially short and ultra short pulse lasers, which from where the pulse duration ranges from nanosecond to femtosecond range. So when we talk about surface functionalization, so we use the lasers to modify the surface properties of the lasers. So this can be achieved by both structuring or texturing at micro or nano scale on metal surfaces or polymers or ceramics. And when we are structuring or texturing the surfaces with the laser, simultaneously, we also modify the chemical composition of the surfaces. So that's how we can change the surface properties of metals and polymers for achieving different functionalities as shown here in the right side of the image. So as we can see here, we can achieve different functionalities such as wetting property. We can change the wetting properties of the material, or we can basically achieve anti-icing functionalities, or there was one question about the holograms. This can be achieved by point-by-point surface oxidation, and we can also change the solar absorptivity of the materials, and antibacterial and cell adhesion properties of the biomaterials, which will be useful in biomedical technologies. And we can also change the emissivity of the surfaces, especially for the space radiators, and we can design microneedles for the drug delivery, and we can also change the drag properties of the surfaces, especially for aerospace applications. So these are all the sectors where laser surface functionalization can be applied, right from automotive, aerospace, electronics, biomedical, healthcare, space, and energy sectors. So in the Syntecs project, we are focusing on especially automotive, electronics, and biomedical sectors, and which I will talk about in the upcoming slides. So when we are talking about micro or nano topographies, so we can't achieve Um, all the scales ranging from less than 1 micron to greater than 200 microns or up to millimeters with a single particular technology. So we have different technologies in place. For example, direct laser writing is one such technology where we can achieve lens scales or topography which are greater than 20 micrometer. Uh, and with laser-induced periodic surface structures, which is a subset of direct laser writing, we can achieve topographies less than 1 micrometer. And there is a gap between 1 micrometer up to 20 micrometers. This can be achieved by direct laser interference patterning technology. So I will talk a bit detail of into a bit detail of these technologies in the next slides. So this is direct laser writing. This is a typical setup of direct laser writing where we have a femtosecond or nanosecond laser source, and the beam passes through the shutter, and the wave plates are meant to change the polarization of light into either circular or linear polarization, and a beam expander to enlarge the size of the beam, and the beam goes to the galvoscan head, which allows us to scan the beam at a particular speed, and there is a telecentric lens which focuses the beam onto the uh, workpiece. So with this kind of direct laser technique or direct laser ablation, what we call, we can ablate the material precisely on both metallic and polymers, even on ceramics, and we can achieve periodic, random, and porous substrate, porous structures. They are both hierarchical structures because it contains both micro and nano topographies as shown here in the following SEM images. So these are some of the structures which are formed by direct laser ablation. As you can see, these are a array of pores, and these are array of dimples, and these are array of ribs or channels. So this kind of periodic surfaces topographies we can achieve through direct laser ablation using a different type of scanning strategies. And when we achieve this kind of micro or nano topographies, uh, this will result in different functionalities of the surfaces as explained in the previous slide. So with this technology, the minimum feature size is defined roughly by the what is the focus spot size which we can achieve on the substrate. The focus spot size is directly proportional to the wavelength and focal length of this lens, and also the incoming diameter, as you can see here. So if we take roughly the wavelength of the laser source is about 550 nanometer, and we use a focal a lens with a focal distance of about 100 millimeter, and an incoming beam has a diameter of 5 millimeter, we can get roughly a spot diameter of 20 microns. So as I mentioned in the previous slide, so we can achieve surface structures precisely greater than 20 micron with direct laser writing. Of course, if we can reduce the wavelengths to UV, we can also reduce the spot diameter, and thus we can get even feature size even less than 20 microns. So and the next technology which I would like to talk about is laser-induced periodic surface structures, which is a subset of nothing but laser direct writing. Instead of ablating the material, we operate when we operate the fluence at the ablation threshold of the material, as these kind of self-organized structures will be formed on metallics and polymer surfaces. So the orientation of these structures and the geometry of the structures is a function of the polarization. As mentioned here, we can change the polarization into circular or linear ones using the wave plates. And with this kind of manipulation, we can achieve grating type of structures or simply nano bumps on the surface. So especially the lips have two types. One is called low spatial frequency lips, and another one is high spatial frequency lips. As shown in these images, these gratings have a periodicity near to the wavelength of the material. For example, if we are using a wavelength of near infrared, which is 1030 nanometers, we can achieve a periodicity of about 800 to 900 nanometers. And if we are using a green wavelength, which is 550 nanometers, as shown here, we can achieve LIPS in the range of 400 to 500 nanometer periodicity. There are also other subset, which is called high spatial frequency LIPS. These can be less than about 100 nanometers in the periodicity. However, LSFL are most popular ones, which because they are consistently formed on the surfaces, and and as you can see here, different since these structures are basically in the nanometric regime, we can get different light diffraction effects as shown in this image. And in order to bridge the gap between LIPS and direct laser writing, we have something called direct laser interference patterning. So here, uh, instead of using a single beam, the beam can be split into two or three beams, as shown here, and a prism will be prism helps to paralyze the beam onto the lens, and finally the lens will converge the splitted beam onto the surface where we can have interference of two or three beams, as shown here. So with this kind of superimposition and interference of two laser beams, we can get different periodic surfaces, and the periodicity of these structures is defined by this particular relation, where it is directly proportional to the wavelength of the laser beam and also the angle between the superimposed beams. So with this technology, we can achieve structures ranging from 1 to 20 micrometer, and the SEM images of these structures are shown here. This can give an idea about what kind of structures we can get. And also, if we use two beams, we can get line type of structures. And if we use more than two beams, like 3 or 4 or 5, we can get different diffraction patterns and different micro and microtopographies. So the one particular advantage of DLIP is basically it has large depth of focus, so it is not susceptible like direct laser writing. That means we have a large degree of freedom when we are operating on surfaces with slight curvatures. So when we talk about competing technologies, which are already existing in the industry. So this table gives a summary of different technologies which are used in the industries I mentioned before, such as automotive or aerospace and biomedical sectors. So as I talked in the previous slides, laser surface texturing is all about changing the surface properties of the material by structuring or texturing the materials from the nanometric to micrometric scales, and also simultaneously changing the surface chemical composition. So although it is in the nascent stage, for example, the laser surface texturing right now in the development of applying into 3D surfaces or large surfaces, and there are some issues with the throughput. So those challenges are being presently addressed, but these are some of the technologies which are already in place industry for decades. So, for example, if we talk about chemical etching, so this is one of the technology in the automotive sector when we talk about etching the molds for injection molding, and particularly for the automotive interiors. And there are another popular technology, so something like electro discharge machining. And we also know the electrochemical machining, where we can achieve micro or nanotopographies on particular metals. And the main shortcoming of these technologies are basically the compatibility with some of the metals only, and it can't be applied to all the materials. So and another predominantly used technique is coatings, which are mainly epoxy or silane or nanoparticle coatings. So with the help of these coatings, we can achieve different functionalities, especially in the biomedical sector. When we use the silver nanoparticles, it can impart antibacterial properties. And there is another method which is micromilling, and although it is not industrially so relevant, still it does some job in some of the sectors efficiently. So, so what is the shortcoming of these particular technologies when compared to the laser surface texturing. So the first thing, the Syntex project is all about sustainable manufacturing. So how we can reduce the environmentally harmful chemicals, both for the workforce and for also for the environment. So with these technologies, as you can see in this table, we have a different type of waste products. For example, if we take chemical etching, there we have to use a lot of etchants like ferric chloride or HCl, and water is abundantly used in chemical etching. And in most of these technologies, a lot of consumables or waste products are produced, such as dielectrics, electrolytes, chemicals, and cutting fluids. So these are really environmentally harmful, both for the users of the machines as well as for the environment. So laser texturing, surface texturing can replace these technologies as it is a clean manufacturing technique, since it doesn't use any consumables and it doesn't cause any waste products. So what we are doing here in Syntex. So one of the key objectives of Syntex is to replace these particular technologies which are already used in the industry. So we have three particular use cases in Syntex. One is the automotive use case, another one is the biomedical, and another one is in the electronic sector. So I'll go one by one into these use cases. However, I will focus on electronics use case in this particular presentation. So the first one is automotive use case. The component which we are trying to texture here is a mold for the automotive interior. So these are the mold is an injection mold, and certain plastics will be injection molded for the automotive interiors, and it has particular texture. And the functionality that is sought here is the scratch resistance of the polymers, and also it has to give antimicrobial properties. And for the part, this is for the plastic part, and for the mold, we are targeting friction and wear reduction to improve the number of components we can produce out of the mold. So as I said before, the current treatment is chemical etching in order to achieve micro nano topographies for these automotive interiors. And on these chemical etched molds, DLC coating is applied in order to increase the lifetime of the etched textures, and also for the ease of demolding. So the challenge is high melt flow resistance, which is caused by the recycled polymers. So this is so the, in order to reduce the injection molding pressure by 21%, we are planning to use the laser texturing for these particular automotive molds. And there is another challenge when we use the chemical etched molds. We can't really transfer the texture completely onto the plastic parts. So this is one of the challenge we want to address with the laser surface texturing. That is to produce 100% texture transfer efficiency with the laser surface texturing. So another use case is orthopedic hip implant. So presently the challenge is problems related to fixation and loosening and stability and biomechanics, and that leads to reduced implant lifetime. So on the medical implant, the functionality what we are seeking is antimicrobial functionality on different parts of the implant, and also hydrophobic surfaces, and also mirror surface finish in particular parts of the orthopedic implant. So the current treatment to produce these particular hip implants is grid blasting and cleaning and masking and sintering of particular titanium based micro nanoparticle powder onto the hip implant. So so in the um, uh, in the Syntex project, we want to achieve different surface roughness levels on the hip implant system using laser surface texturing, and also We would like to decrease the microbial attachment by tool lock, and also replace all these processes by single step laser surface texturing treatment. So, and the third use case, which I want to particularly focus in this presentation, is complex shaped vapor chamber. So the challenge is vapor chambers. We know they are found in most of the electronic systems. Even if you take iPhone and open up, you will find a vapor chamber in order to cool the electronics in the phone. So so this is a simple system. It's a flat vapor chamber which is available in the phones. But if you are talking about something called graphic processing units in Intel and other workstations, these particular GPUs are have complex shapes, and the vapor chamber should be conformed to these complex shapes. So so there is a demand for more complex shaped vapor chambers in the market, and current technologies such as bonding and sintering of porous copper powder and mesh, and using a spacer to vacuum seal and bend into the shape has a certain kind of limitations on first is like how the shape first on the shape, as well as it is quite energy intensive process when we are talking about sintering of porous copper powder or mesh. So we want to replace this particular treatment method with the laser surface texturing in the Syntecs project. And the functionality what we are seeking is to improve the thermal efficiency of the designed vapor chamber. And these are the objectives in order to improve the cooling efficiency by 48%, and also replace these technologies by laser surface texturing. So I'll talk a bit more about this particular use case in the upcoming slides. So this is one of the case studies, as I mentioned before. So uh, this is the vapor chamber, as I was mentioned. It is predominantly used in the electronics. Using the two-phase heat transfer technique, it can take the heat from the electronics and rejects into the heat sink. So this is one way of rejecting the uh, heat to the surroundings, and it is a reasonably efficient way at the moment in small scale electronics. So as I mentioned before, the challenge is demand for more complex shaped vapor chambers for the GPUs in order to transport heat from hot surfaces to the heatsink assemblies. So with the existing manufacturing techniques, we have the limitations of geometry, and they require high energy surface treatment steps. So as mentioned here. And the KPIs for this particular use case is to improve the cooling efficiency, as I mentioned before, and we want to replace the existing treatment techniques with the laser surface texturing. So, so how we have achieved, or is being achieved in this particular Syntex project. So, uh, generally, the internal surfaces of vapor chamber have either wire or powder, and where the liquid is, and there is a liquid in between the two plates, and where the heat is taken from the electronics, the liquid wicks through these surfaces uh, uh, okay, and goes on condensation and evaporation cycles. So uh, so we want to emulate internal structure of a complex vapor chamber with laser surface texturing, and in order to do so, we had discussions with the end user, and we also did the literature review, and we found out that the desired surface texture for capillary wicking phenomena is narrow hierarchical post with high aspect ratio on these internal copper surfaces. So we want to achieve this kind of topographies with two technologies. One is with direct laser writing by using the femtosecond lasers, and another one is direct laser interference patterning with the picosecond laser processing. So, and when we use direct laser writing, as have shown in the SEM images before, we can get, we can obtain hierarchical topographies. And hierarchical, what I mean here is On top of micro topographies, we can also get laser-induced periodic structures or nanoparticle deposit as side effects. So we thought that these kind of hierarchical structures will help in capillary baking phenomena. So with the femtosecond laser processing, as shown here, we can achieve scales from 20 to 200 nanometer, and also with as the laser induced periodic structures are basically the side effect of the process, we can achieve scales less than 1 micrometer with this particular processing technique. And with the DLIP, we can bridge the gap as shown here. So we have produced structures with spacing from 4 to 20 micrometer. And since we are using picosecond lasers, we also get laser-induced periodic surface structures as side effect, and they have also the periodicity less than 1 micrometer. So we used so these are uh, this table gives the overview of different process parameters we used to produce micro and nano topographies for this particular case study. As you can see here, for the direct laser writing, we used femtosecond laser source, which is 10 watts and has a wavelength of 1030 nanometer. And for the DLIP, we used 12 picosecond laser source, 300 watt, and a wavelength of 1064 nanometer. So this is a vapor chamber along with the heat pipes, which will be used to uh, which will used as a heat sink for graphic processing units. And these are some of the images for this particular flat plate vapor chamber, how they look like. And so this flow chart gives what we are doing in this particular case study using direct laser writing and DLIP. We will first texture the surfaces, and we use post treatments such as humidification, oxygen plasma, or nitric acid cleaning to treat the surfaces to in order to surface to achieve hydrophilic properties. And finally, once these samples will be sent to capillary performance tests where we can measure capillary rise versus time. And with the feedback from this, we can optimize the parameters for direct laser writing and DLIP texturing. And finally, once the parameter optimization is done, we will send these particular coupons for vapor chamber heat transfer tests. So these are some of the images with the when we textured the copper with the femtosecond direct laser writing technique. So as mentioned before, we wanted to achieve hierarchical pose from spacings from 50 to 200 micrometer as shown here. And as you can see from these images, uh, lips are formed on top of these particular pillars as side effect. And also in between the grooves, we can see porous micro or nanoporous structures. So uh, and these are the coupons generated from direct laser writing for conducting the capillary performance tests. And and uh, and these are the structures which are fabricated from direct laser interference patterning, and these have a spacing from 4 to 10, and also a depth of 2 to 5 micrometers. And as you can see, these particular surfaces are also covered with the laser induced periodic surface structures. So essentially, with both DLIP and DLW, we have covered scales from less than 1 micrometer to up to 200 micrometers, and we wanted to investigate how these particular structures will helpful in capillary wicking performance. So once the laser processing is done, uh, basically all the surfaces will exhibit hydrophobic properties over a period of time. So we have attempted some of the post-treatment techniques such as humidification, oxygen plasma treatment, and nitric acid cleaning. Each and every technique has it has their own advantages and disadvantages. For example, humidification. The humidification, we achieved contact angles less than 50 degrees, and they were stable up to 2 weeks, but gradually they became hydrophobic after exposed to air. and there was some kind of morphology change in some areas. So we did not select this particular technique for as a post-treatment technique, and instead we used oxygen plasma treatment because this is quick process, and also continuous storage is not required, and there was no morphology change observed on the surfaces. And there is another technique called nitric acid cleaning, which is used to clean the oxide layers on the surface. So uh, uh, which is also a quite quick process, and the properties are quite stable for few days with this nitric acid cleaning. So we have used these two post-treatment techniques to impart hydrophilic properties for on the laser-treated copper surfaces. And with that, we have started conducting the trials for capillary rise versus height experiments. So, as I mentioned before, this is a typical vapor chamber consisting of a wire mesh. So, initially, the capillary rise experiments are conducted on these particular vapor chambers. As you can see, when we open up the vapor chamber, it consists of two plates, the top and bottom plates, and each plate has a wire mesh embedded for the capillary wicking of liquid inside these internal surfaces. And each surface has a different wire thickness and mesh size. As you can see, these are some of the snapshots from thermal image camera, which shows the capillary height on the top and bottom place. It is evident that lesser the aperture, which is 0.07 or 70 micrometer, we obtained more height with the capillary rise, and when the aperture is size is more, we got less rise in the capillary phenomena. So we carried out the test on the laser textured surfaces too, and these are some of the snapshots, and these are some of the snapshots from the thermal camera at different time intervals. And this plot shows for different spacings and depths what is the capillary height with respect to time. As we can see with the lower depth, which is 25 microns, there was literally no wicking. And when the spacing was less than 125 microns, we got better performance in terms of capillary height with respect to time. And also when also on the D-lip surfaces, which are quite a bit shallow compared to direct laser writing surfaces, as shown here, uh, we got no wicking performance on D-lip surfaces. So essentially, direct laser writing written surfaces with higher depth and lesser spacing perform better. And in terms of post treatment, we were talking about oxygen plasma and nitric acid cleaning. So in order to understand the repeatability of this capillary rise experiments, um, we have done experiments on both oxygen plasma treated and the nitric acid clean surfaces. And as we can see, oxygen plasma showed poor repeatability, and nitric acid clean surfaces have shown good repeatability uh, of these capillary performance. And also, what we observed was with by cleaning surfaces with nitric acid, uh, the copper loose particles will be removed on the surfaces, so there won't be any effect on other micro or nano topography spore produced by the laser surface texturing. So yeah, in conclusion, so in the Syntecs, we demonstrate a digital and green laser surface texturing approach to generate complex multifunctional surfaces. So we have shown that we can replace environmentally hazard chemical treatments such as coatings, etching, and high energy thermal and mechanical treatments such as sintering and blasting, grid blasting and grinding techniques with laser surface texturing to achieve particular functionalities. And we can achieve full scale of surface textures greater than zero point 0.5 micrometer with both direct laser writing and DLIP technologies, which can be utilized for surface design in automotive, biomedical, and electronic sectors. Direct laser textures, along with appropriate post treatment technologies, to impart hydrophilic properties have shown to improve the wicking performance on the copper surfaces. So these are some of the conclusions drawn from this presentation. And with that, yeah, I conclude my presentation. And if you have any questions, yeah.
Thank you very much, Avesh, for your presentation. Let's see if there is any questions or comments. I see a hand raised. Muhammad Azak Arshad, please, if you want to ask the question. You are muted, sorry.
Can you hear me now?
Yes.
Yeah, all right. Thank you for the nice presentation. I just have maybe a question about the topic because given the title of your presentation, also the project title about sustainability and digitally driven texturing, I didn't really see those aspects in the presentation.
Oh, yeah, the digital aspects will be probably covered in the next presentation. So I will be quiet about this. Maybe this and the green part I can answer because as I mentioned before, uh, the current treatment technologies used in the industry are these chemical etching, electro discharge machining, and coatings and micromilling. These are some of the technologies which are already in place. And when we are using these technologies, there are so many waste products such as HNs and dielectrics and electrolytes from these particular technologies. Uh, Laser texturing can replace these technologies because it doesn't produce any consumables essentially. Uh, any chemicals or it doesn't consume except water, which is also marginal for maintaining the chillers. There are no waste products arise from laser surface texturing. So in terms of that, we can say that laser surface texturing is a clean and green manufacturing technology compared to these particular technologies. And probably there is one more aspect, which is electricity consumption. And I think life cycle analysis modeling will help us to understand where it stands with respect to these technologies. And probably in the next presentation, I hope it will be covered a bit. Uh, yeah, I
Yeah,
yeah, I'm not sure if yeah.
yeah, because that's just my main question. Like if you have or your consortium did a sustainability study with these competing processes, because there are some like bold statements uh, in your project about the generation of chemicals. Like for example, if we specifically talk about electrochemical machining, like the salts mentioned also in the slides they're like neutral salts, like table salt, for example, in water. And if we specifically talk about texturing, the consumption of electrolyte is quite low, which is also recycled. So were these aspects taken into account when making these claims, or is there any
The,
literature that can
understand
be?
completely.
Yeah.
Uh, Probably in the consortium, we have three use cases. In these three use cases, so the competing technologies for chemical etching, which is for the automotive use case, as I mentioned here, and for the medical, it is not the surface treatment, but it is like the grid blasting and cleaning, and it's like replacing multiple steps in the process chain with the laser surface texturing. And that is one thing. And it also porocoat sintering is basically high energy intensive process. And also in the electronic sector, we are talking about bonding and sintering of porous copper powder onto the surfaces. So this is again a high energy intensive step. So I think we have focused on these particular aspects, for example, the chemical etching and also high energy intensive steps and replacing these with the laser texturing. So in terms of that, I can, we are saying that it's a green technology compared to the existing ones. Yeah, and again, these are only taken from the literature, and the statements are partly applicable. As I said, with the laser surface texturing, we literally don't have any consumables or base products. Uh, uh, but only in terms of electricity consumption we might have we need to see where it stands with respect to these technologies. So yeah, maybe we can't really say 100% it's a green technology, but with respect to some of these technologies, yeah, it can be what you call partially green, maybe. So yeah.
Yeah, because in the slides you mentioned that you do not use toxic chemicals, and then in the last slide, the case study was that you have to use the nitric acid for cleaning. So
Yeah, yes. So
that's
we
just
do
a bit,
have
yeah.
this kind of yeah. This is one of the questions we always had in the. So that is the reason we have used different types of post-treatment technologies. Again, this is case study specific, and the nitric acid cleaning is already existing in the process chain of cleaning the vapor chambers. So we thought that yes, it's when it is already existing in the process chain of cleaning the surfaces of the vapor chambers. So we are just simply taking the step for we are just importing the step in the process chain in order to give the benefit or imparting the hydrophilic properties. So
So
yeah.
so it's really like application specific that you have these case studies, I guess, for the comparison with the green aspect and the digital aspect.
Um, I would say yes for this thing, but in general, yeah, maybe there are some other projects in the this particular call which are focusing on the sustainability. Probably they are focusing on different use cases, uh, which are which are uh, give more idea about they can give more idea about what are the um, other particular functionalities they are targeting, and how it can be called as green.
Right. No, perfect. Thank you so much.
Thank you. Let's see if we have another questions. Yes. Yeah, please.
Uh, Hi, Anvesh. Uh, yeah, thanks for the very nice presentation. It's really very comprehensive. I just have a quick question on your second. You mean you didn't talk much about the second case study, but how do
Yeah.
you achieve uh, mirror finish with texturing? Isn't it contradictory?
Yeah. So this is about not the mirror finish, I would say. What we call is uh, those are additively manufactured parts.
Mm,
So basically, we are trying to polish those parts with the nanosecond laser processing in some cases.
mm,
So in order to remove the surface, in order to reduce the surface finish on those particular parts, but still
mm,
it's far from what we are trying to say here. It is like
mm.
try to achieve the mirror finish with lasers is like one of the objectives, but probably we cannot achieve with the lasers. We are only trying to roughen the surface to achieve particular roughness, which is useful for attaching this particular porocoat, or also achieving other functionalities such as microbial resistance or something like that. But
Mm.
mirror finish is one of the functionality we wanted to, but yeah, it's obviously it is difficult to achieve
Okay, so it's still
in the
laser
context
polishing
of
with a nanosecond. Yeah, okay, yeah.
yes, in the context of what you call reducing the roughness of
Mm.
additively manufactured components.
Okay, yeah, I get it. If I have time, I will just ask another quick question.
Yep.
Was there any oxidation after texturing of the copper parts that you have textured?
Yes, absolutely. Yeah, it is obviously the copper surfaces get oxidized, and uh, the thing is, we are using femtosecond laser machining, but doesn't matter. We are using high power, high fluence here. So the surfaces get oxidized, and most of these oxide are either cupric or copper oxide. Generally, immediately after laser texturing, we can see the formation of cupric oxide, which is CEO, which is
Mm,
nothing but hydrophilic in nature. And
mm,
when we expose to air, this CuO reduces to hydrophobic Cu2O, and that is the
mm,
reason we are getting the hydrophobic properties of these laser texture surfaces. But the main challenge is how to stop this transformation from hydrophilic to hydrophobic, because for the capillary wicking performance, we need hydrophilicity. So that is the reason we are attempting different post-treatment technologies here, as shown in this table.
okay, yeah, thanks, Anvesh. Yeah.
Thank you.
Okay, let's See, there is another question. If not, yes, please, Molojeta.
Okay, thank you so much for the interesting presentation. Can you hear me?
Yes.
Yep.
Okay, I may have like two questions. The first is like what characteristics of the surface textures, mainly like the area enhancement, the wicking ability, or the hydrophobicity is in charge of this heat transfer enhancement? That's my
I
first
think,
question.
yeah. So
Uh,
to answer the first question, it is the hydrophilicity is a prerequisite for capillary wicking performance. And also, uh, when the surfaces are hydrophilic, there will be more surface area for the heat transfer process. So I would say that hydrophilicity is the main thing we are looking at. And these are the post-treatment technologies after laser processing. We are attempting to impart the hydrophilic properties or prolong the hydrophilic properties of the laser textured surfaces.
so wasn't the plain surface more hydrophilic than the laser textured ones? Because in most cases, the plain surfaces are more hydrophilic. So
Not really. On the plane surface of copper, the contact angle is about 60 degrees to 70 degrees. So immediately after the laser texturing, the contact angle, what we can observe is literally zero. That means when you put the droplet, it simply spreads on the surfaces. And that is a reason if the contact angle is not a zero, we cannot see this kind of wicking on the surfaces very quickly in less than 10 minutes. So, for example, um, if the contact angle is above 30 degrees, then what we can say is 30 or 40 degrees. We cannot see the wicking performance on laser texture surfaces. So, what we need here is a contact angle of really less than 10 degrees. That means laser texturing can help initially in order to achieve that contact angle, but once it exposed to the air because of the oxide transformation, and within 2 weeks it will become super hydrophobic in nature. So we wanted to suppress that kind of transformation with these kind of post treatment technologies.
yes, I agree. So don't you think like the role of the surface textures that are induced by the laser are being taken
Mhm.
over by the chemistry, mainly the oxide layer formation, and the oxide layer
Yes,
formation is in charge of the.
I agree. Yes, I agree completely with this point. So it is only use case specific, to be honest. When we talk about other use cases, for example, yeah. So for example, for the automotive use case, hydrophilicity is not an important parameter. There are some other functionalities we are looking at, and we didn't have any other post-treatment technologies needed to apply for the automotive or biomedical use case. But in the electronics use case, especially since the hydrophilicity is the prerequisite, we had to go with one of the post-treatment technologies as shown here. And there is no workaround, to be honest, in order to achieve that particular functionality. And since this nitric acid cleaning is, as previously mentioned, it is already in the existing process chain of fabricating this vapor chambers. We just imported this particular step from the process chain and used it on the surfaces. So we are not really introducing a new step in the process chain in order to achieve this particular functionality. So in that way, we can say that, okay, uh, we are achieving what we wanted to achieve, but at the same time, uh, not with the help of, again, with the help of surface chemistry, obviously, as you said.
Okay. Yeah, just I was wondering because like this, if we do same study in other materials, I'm not sure if we'll have same response. I felt like this is more like material dependent as copper is prone to
Uh,
oxidation.
to
That's
be
what
honest,
my.
most of the metals immediately after the laser texturing, they become hydrophilic, but over a period of time, they will become super hydrophobic
Okay.
because of, and some of the, for example, if we keep them under the water, we can suppress the transformation or chemical transformation on the surfaces, but it may also prone to corrosion. So we don't want
Okay.
to attempt those kind of things in this particular case study.
Okay. Just to save time, I'll go to my last question. because
Yeah.
you mentioned like because the geometry is also a bit complex, there are some curvy surfaces on the edges and stuff. So how did you
Yeah.
treat those edges, or like which I would call them like with some incidence angle, or when you texture? Because you didn't discuss those parts on your SM image.
Yes. So yeah, I understand completely. So far, what we presented here is on the flat surfaces, and this is only one particular part of the Syntecs project. And I would say that, especially at the moment, we are using a 5-axis stage in order to treat these particular curved parts here, for example, especially in the Z direction. So in our facility, we have both 5-axis machining and also simultaneous movement of both the axes in order to reduce the time of processing on the curved surfaces, where we can keep the machining surface normal to the incident beam. So that is one way we will be achieving surface texturing on these intricate geometries, which are especially in the curved in the Z direction. And what we do is we initially we split the surfaces into number of fields, and we process those fields especially, and those fields are less than the critical curvature, so that critical curvature of at that particular location, and with that we are trying to minimize the disturbances such as focal offset on these particular surfaces. So yeah, that is that work has been taken care by one of the other work packages in the Syntecs project. But here mostly we are on the technology development side, where we are trying to process on the flat coupons at the moment.
Okay, thank you.
Thank you. So we will go to the last question because we have to move to another topic, another speaker. So before going to this question, if you have additional questions, please write in the chat and we can write our answer to you. So final question, Yavor Sofronov, please, if you would like to ask something.
Hello, thank you very much for the interesting presentation. I would like to ask, is the initial roughness of the coupons affect the laser treatment, or if there is, what is the initial roughness of the coupons?
So as I mentioned here, the coupons have initial roughness of about 0.31 micrometer. So unless here we are focusing on topographies which are 25 to 75 micron deep, and the spacing of about 50 to 200 micrometers. So the initial roughness doesn't really affect when we are targeting such kind of topographies, especially those are when they're deep. But if we are trying to achieve laser-induced periodic surface structures, which are especially in the submicron scale, the initial roughness really affect the formation of these kind of submicron structures, since they are self-organized and we don't have 100% control on formation of those structures.
Thank you very much.